Welcome to D-Physics. I'm Daniel and today we are going to review the interference phenomenon between two electromagnetic fields. So let's imagine that at some point in space and time let's imagine at this point called R, and this is our reference system. Let's imagine that at this point we have the superposition of two electromagnetic fields. So let's imagine we have the field E1 at this point in time and the electric field E2 at the same point and at the same time. So we will have that because of superposition of electric fields, the total electric field at the point R and time t is described by the sum of the two electromagnetic fields at that point. Now, what we want to study is the intensity of the electromagnetic field at that point. So we have that the intensity, which is a scalar function of R and T, is equal to C, the speed of light, and epsilon 0, which is the permittivity of space, times the average, the temporal average of the square of the electromagnetic field at that point. That means we have to multiply the electric field at that point times its conjugate. Because remember that the electromagnetic field is a complex function. And the brackets means the temporal average of the electromagnetic field at that point. Remember that this electric field is the total electric field at that point, which is the sum of the first electric field plus the second electric field. Now what we have to do is to replace the value of the total electric field in terms of the electric field 1 and 2 in the intensity function. So if we look at that, we'll find that the intensity at that point can be regarded as follows. So this first term is the intensity of the first electric field at that point. What is more, we will have another similar term but with the second electric field at that point. So this second term is the intensity of the electromagnetic field of the second electromagnetic field at that point. Remember that the brackets means the temporal average in that point of space. But we will find out also two more terms, which are the combination of the two electric fields. So we will have electric field 1 at that point times the complex conjugate of the second electric field also at that point, remember, and we'll find another term which is similar but the complex conjugate. So we have the second electric field times the complex conjugate of the first electric field. So we'll have that intensity is the intensity of the first electric field plus the intensity of the second electric field plus two terms which are called the interference terms. But now we can see that these two terms are similar, just that this one is the complex conjugate of this term. So we have, these are complex numbers, complex functions. So here we have the complex function plus its conjugate. So if we use a property of complex numbers or complex functions, we will find out that this term is 2 times the real part of this term. If you have any questions about it, let me know in the comments. So let me explain that a little bit more. Imagine we have this complex number or this complex function, and here we have its real part and its imaginary part, and let's imagine that we sum the complex function plus its conjugate. So what we have would be a plus I times b plus its conjugate, which is a minus I times b. So we have that these two terms cancels out, and we have 2 times a, which is 2 times the real part of the complex function or complex number. Now let's go back to our expression of the intensity. So we have that the intensity at the point r and time t is the intensity of the first electric field at that point plus the intensity of the second electric field at that point plus the interference term, which is c times epsilon 0 times the real part of the time average of the electric field 1 times the electric field 2 its complex conjugate at that point. What we have to do now is to solve out this term. So in order to do that, let's consider the two electromagnetic waves to be two harmonic waves with linear polarization. That is, E1 is equal to an amplitude at the position r times a phase at that point times a temporal phase. So this is the first electric field, and we have that it is linearly polarized, so this vector represents the polarization of this electromagnetic wave. The same for the second one. Now we calculate the time average of the multiplication. Remember that this multiplication of this vector represents the inner product or the dot product. So this multiplication is equal to the multiplication of the amplitudes at that point times the dot product of the polarization of the two electromagnetic waves times the phase, which is phi1 minus phi2 times the time average of this harmonic function, which is e to the I multiplied by omega 2 minus omega 1 times t, and all these terms are not in the time average because they don't depend on the time, so we can put them out of the time average integral. Now we have that in order to this term to be different from 0, we will require that omega 2 is equal to omega 1. So we have that this function, the time average of this function, is equal to 0 if omega 2 is different from omega 1, and 1 if omega 2 is equal to omega 1.